Welcome to the presentation of our paper titled Intrusion Detection Systems Enabled Power Electronics for Unmanned Aerial Vehicles. It is a concept paper on a collaborative work between faculty members from 3 universities: Florida International University, University of Alabama in Huntsville, University of Alabama, Tuscaloosa. In the modern semiconductor supply chain, there are several parties involved, from design to fabrications to distributions. The intellectual property moves all over the world, like from China, especially from China to US, and this is currently we are seeing a lot. The intellectual property, as it moves from in different formats like design, physical layout, and in this chain, there can be different group of attacks possible, like an untrusted party can include hardware Trojan, counterfeit ICs, they can do like a piracy and many other things. Hardware Trojan is very one of the severe issues that we can see recently. It is a circuit that can be inserted by a third party to take the control of the whole system at some point when the system is in use. It is like a circuitry that will trigger when a special scenario appears. Maybe that may be even based on the timing. So more than that, an untrusted party can include like a malicious circuitry in order to steal information from the system or shut down the system, or like a different measure that is completely unoptimal and maybe malicious with respect to the mission. If you can see, there are different reports has been published on this group of security issues. In this work, we focus on power electronics of unmanned aerial vehicle. UAVs are increasingly being used for remote surveillance as well as data collection. Recently, we are seeing its uses for the package delivery, and there are many more uses that we can expect in the near future. And this is an example of hardware, UAV hardware. This is PX4, a popular open flight control software. It includes drivers for different types of sensors, sensor fusion algorithms, feedback control algorithms, and many other things. And if you see that this PX4 firmware, it runs on a host operating system, and this operating system provides message bus that is do the communication between different components of this firmware, drivers and others. So for like here, flight controllers, drivers, external connectivity, also like data logging. So the decisions taken by the flight control system that goes to the ESC, that is electronic speed controller, it is associated with each motor of this quadcopter. Here this is an example of PX4 for a quadcopter. So this ESC is another firmware, like a very low level firmware that is running the motor for each rotor. So this PWM signal, that is pulse width modulation, it is actually controlling the speed of the motors through on and off time of the signal. So it controls the average value of the signal, and according to it, this ESC firmware that control the speed of the motors. So here is the detailed picture of flight controller. So this controller gets inputs from various sensors, most of which are on board. So the sensors, it has like a magnetometer, accelerometer, gyroscope, barometer, GPS, etc. that we can see in the figure. So these measurements can pass through an an extended Kalman filter that reliably estimate different input parameters for a series of control submodules. For example, position control, speed control, orientation control, and at the end, the angular rate control. So this control structure also takes remote pilot commands or as well as like a trajectory paths as inputs. These inputs usually comes from the base station, or it may come from the neighboring UVs, especially in the case of a collaborative swarm. So the angular rate control submodule sends the control commands in the format of PWM to the inverters, that is the motors associated with the four rotors in this case. So here is more about pulse width modulation. So a motor responds according to the average of the PWM pulses, and its speed depends on the duty cycle and the frequency of the PWM signals. So a system can run fast or slow based by changing this duty cycle as well as the this frequency. So if you see in this figure below this 75% duty cycle, the motor with this duty cycle will run faster than other two. Similarly, the 25% duty cycle will make the associated rotor to run like a slowest compared to the others. Here we list our various types of attacks on UVs. The first kind is the false data injection to the sensor data, like any other sensor data-based closed-loop controls. So an attacker can change one or multiple measurements here, and it can be random or intelligently planned. The latter kind is severe as it tries to bypass any hindrance like data validation, methodology, or any kind of estimation, prediction mechanisms, or it can create a specific impact that the attacker wants to achieve on the target. However, it is harder for an attacker to launch as it needs more knowledge and capability. The second kind is the firmware attacks. Malicious attackers can insert malware in the system firmware to take partial or like a full control. So in this case, they can modify the input and output of the controller to achieve their goal. The last kind is the hardware Trojans, as we discussed initially. The existence of hardware Trojan is hard to test or like a validated, and that it is hardware Trojan free. And it is like, as you said, it is a special circuit that is triggered often like a rare cases. So from the input and output of a device, it is harder to understand whether it has any hardware Trojan. So once it is triggered, the on-time and off-time of a PWM signal can be maliciously modified to result in an undesired behavior. Here we'll talk about PWM control circuit and potential hardware Trojans. So this circuit generates PWM signals according to the inputs from the flight controller. So the figure that you see here, this is TL494, a PWM control circuit on a single chip. And as you can see, a change in RT and CT can change the frequency of PWM signal, and which will ultimately change the motor's speed. Trojan can be inserted in DTC comparator that will change the PWM duty cycle and so the speed of the motor. The Trojans can be inserted similarly to error amplifiers as well as PWM comparator. So these will ultimately impact the speed of the motor. So Trojans can be inserted more in these like logic gates, flip-flops, etc. to create a different duty cycle. As we have seen, an UAV can be attacked from different level of the control, very top from the sensor data up to the hardware Trojan. We propose three layer of intrusion detection systems to defend it from any potential intrusions. So we want to deploy them in three layers, namely at the controller level, that is the firmware operating system, uh, then the communication channel between the controller and the inverters, that is to the ESC from the PWM signal generators. And the last one is at the individual inverter or ESC level. And according to its level of deployment, the capability of this intrusion detection will be defined. So in the next few slides, we'll talk about how we want to train these intrusion detection systems. We will implement our proposed intrusion detection system exploiting different patterns. So we see a pattern between the input and output of the flight controller. We expect a pattern between duty cycles and the flight controller's control commands. So the PWM signals and the ESC generated modulations, they will have a relationship. So we will exploit these three kind of patterns basically. We will learn using the normal data, and if we consider like a PWM signals, we can talk about three different kind of data sets, three different kind of trainings. So the first kind can be the valid PWM signals. Second one, the relationship between PWM signals to different inverters, that is different motors. And lastly, we can talk about the conjugative PWM signals, the relationship they have between different like a time frame PWM signals. So we will train using the bad data as well, but the attack data set will be limited compared to the good data set because we will implement this attack and collect the data. Since implementing many scenarios is very much like expensive and time consuming, so we will not be able to like collect as much as data that we can do for the good behavior, that is just normal behavior and easy to collect the data. So our data set will include sensor measurements and corresponding control decisions. So the magnetometer, accelerometer, gyroscopes are many on board, as well as the external sensor measurements will be considered. We will consider duty cycle, that is the PWM signals, and also the ESC generated signals. And as you said, like our features will be both normal and attack cases. So our three layer of intrusion detection system will work comparing their respective behavior. So in case of at the controller level, our anomaly detection will classify good and bad, considering a control decision with respect to control inputs. At the PWM communication channel, the attack detection will consider inconsistency of the PWM information with respect to the controller generated control commands. And we'll use digital signal processing to recover duty cycle information. And in case of ESC level, the attack detection will happen comparing the PWM signals and the ESC generated modulation signals. And having attack data in our training, we will be able to reduce the false alarms, as we will be able to see in the next slide. The good data could be enough to generate these intrusion detection systems. To train our intrusion detection system, especially at the controller and the PWM generator level, we will use support vector machine based novelty detection technique. So this support vector machine, that is SVM, there can be different kind of kernels. So we will use here the 2-class SVM. Although 1-class SVM that can do the anomaly detection just using the positive data, they can draw a non-linear boundary around the positive data samples and can find the anomaly. However, the hyperparameters they use, if there is any error in the estimations, it can create overfitting and underfitting issues, and this problem is much higher in case of 1-class SVM than 2-class SVM. So in case of attack detection at the ESC level, we will implement the intrusion detection system using lightweight rule-based mechanism. The reason is also here, like ESC firmware is lightweight, and we cannot deploy anything that is computationally expensive. And so we are very end of our talk. As we said initially, it is a concept paper. Our ongoing work at the level of completing the test-bed design and implementations. So after having these things done, we will collect good data, that is PWM data and corresponding control commands in normal cases. Then we will implement different attack scenarios at different levels and collect the data. Lastly, we will do training and testing of the intrusion detection systems. Thanks for listening. If you have any questions, any queries, please email us. We'll be very happy to answer any concern, any confusions. Thank you. Bye.